let's start to go through this. So if you look at that,
I'm starting brown for sure.
all right, Mara.
I already did.
Going? Okay. So for a spontaneous reaction, delta S of the universe is what? Positive or negative? Positive. Cool with that. For a spontaneous reaction, delta G is negative. Now, so here is the mother of all thermodynamic equations. And if you look on this sheet, there's a whole bunch of different ways that you can calculate delta G. The one we're going to focus on is this one. Delta G equals delta H minus T delta S. And what you'll notice here is that these have like the not values that are under standard conditions, okay? And these values are going to come from the back of the book. So if you look on that appendix on the back of the book, which is going to become your friend, you have three different columns. You have delta G, delta H, delta S. Now, we're going to play through some different scenarios. So the first rule of understanding this equation is that Mother Nature likes a hot mess, or is a hot mess, depending upon how you want to phrase that. Okay? Mother Nature likes a good fireworks show. What that means is that Mother Nature wants two things to happen. She wants it to become more disordered, because she's just chilled out, and she wants an exothermic reaction, because she's old. It's like, I'm cold, baby. Go get me my sweater. Okay? So Mother Nature likes a hot mess. Okay? Start with this idea. Those are the two things that Mother Nature wants. She wants an exothermic reaction, and she wants to make a mess. So, knowing that she wants an exothermic reaction, what's going to be on an exothermic reaction? What's going to be the sign of delta H? Negative. So in an exothermic reaction, I'm going to have a negative delta H. Cool, right? Now, if we're going to make a mess, what's going to be the sign of delta S? Positive. So this combination of negative delta H and positive delta S, this speaks to Mother Nature. Okay, this is her love language. Okay, this is her affirmation. You want to impress Mother Nature, you make a hot mess. Okay, none of this cleaning stuff. I don't want to be code. Okay, Mother Nature wants a hot mess. Now, here's the reason why. If you look at it from a numbers game, okay, so I'm just to make up some numbers. Okay, this is purely just making up numbers. Let's let, I don't know, delta H be 10, and I'm going to let delta S be 20. Okay, I'm just making up numbers. All right, just stay with me. So in situation number one, and I'm going to let the temperature be, I don't know, 30 degrees Kelvin. Now, when you look at your book columns, delta H's, as you all know, are kilojoules per mole. Okay? This is going to be important. When you look up data in your book, your delta H's are kilojoules per mole. Your delta S's, though, are joules per mole Kelvin. Okay? Those are going to be important. And your delta G values are also in kilojoules per mole. So here's the first thing you need to decide. First thing that you need to decide. on this T delta S part, okay, when you get this delta H here, minus T delta S, you need to make a decision. You either roll that delta H into joules, or you roll that delta S into kilojoules, okay? I don't care. Makes me no difference. But you need to make a decision, because I can't add kilojoules to joules. Now, the reason that we multiply by temperature is this, because delta S has units of joules per mole Kelvin. So then when you multiply by Kelvin, then the Kelvin cancels out, and then you're left in joules per mole, which is what delta H is in, which is what delta G is in. Okay? That's why that's the only term that's multiplied by temperature, because that allows us to cancel out that Kelvin, and then we have the same units as the other. So again, the most common mistake that's made, the equation itself is not difficult. Pay attention to the little things. Okay, so here's what I've got. I want to calculate delta G. So I've got my delta H. I'm going to make that negative 10. Okay, we'll put that as kilojoules per mole, minus my temperature of 30. And then I've got my delta S, and let's say that that's positive 20 kilojoules per mole because that way everything's in the same. Now, here's what I want you to see. Mathematically, I'm going to have a negative number here for my delta H minus a positive number, right? So mathematically, is there any way, since this is going to be a negative number here, and I got a positive delta S, and my temperature is always a positive number. So if I have a negative delta H and a positive delta S, when you subtract those numbers, what is always going to be the sign of delta G? Negative number. So this combination is the love language of Mother Nature. This is her love language, because you have an exothermic reaction, like, maybe I'm cold, started a reaction, okay? And you're going to start a reaction that's going to be exothermic. Then, in the process of making the reaction, you're going to make a mess. You're going to spill things in the house, whatever. Mother Nature doesn't care, okay? This is cool, because she's going to get warm, and Mother Nature is going to like this combination. So here's what's important. This negative delta H in combination with this positive delta S will always, always, always produce a spontaneous reaction. So we're going to go through 4 scenarios. If you ever make flashcards, this might be the time. So when you have a negative delta H in combination with a positive delta S, that combination will always produce a negative delta G, which means that that reaction is always spontaneous. Okay? Always spontaneous, right? I say it again. Always spontaneous. No matter what you do, this reaction is going to happen. Even if you go to 0 Kelvin, you still have a negative delta H, which makes it a negative delta G. Okay, so no matter what you do, that combination is always going to produce a spontaneous set of reactions. Now, in contrast to that, we're going to switch the signs. We're going to keep the same numbers. So I'm going to have a positive 10 kilojoules per mole. That's my delta H. Minus 30 degrees Kelvin. But now I'm going to make my delta S be a negative, whatever that was, 20. Okay? What is the sign you're going to get for delta G?
Plus.
Why?
Because negative times negative is positive, plus positive is positive.
So I've got a positive delta H here, minus a negative here, which is I'm going to add that delta S term. There is no way to get negative delta G. So this is where Mother Nature is like the antithesis of her love language. So what's happening here is that you're going to make Mother Nature cold because it's an endothermic reaction, and you got to make her clean. Mother Nature is having no part of this, okay? No part of this. It's like, you want me to get cold and clean. And Mother Nature goes, I'm a hot mess, okay? Clean and cold, that's a bad combination for me. I'm not doing this, okay? I'll do it, but you got to put energy into the system to make it happen. Okay, so now we're going to play a different scenario. Okay, so now I'm going to have a negative delta H. Okay, so that delta H is going to be the negative 30. No, my delta H is, I got to keep the same numbers. 10. Temperature. I'm going to leave the temperature out of this for now. But then I'm going to have a negative delta S, which we said was negative 20. So here's the vocabulary on how you describe this. So the enthalpy term is negative. So Mother Nature is liking this. So how you phrase this is that you say it's driven to spontaneity by enthalpy. Okay? So the enthalpy term is driving it towards spontaneity because it's an exothermic reaction. You have a negative delta S. That's driving it away from spontaneity. So you say, okay, my enthalpy is driving it towards spontaneity. My entropy term is driving it away from spontaneity because I got a negative delta S and a negative delta H. So I have two conflicting ideas. Part of this is going towards spontaneity, part of it isn't. So what you want to do is find an equilibrium temperature. This is where you have like a phase change, like you're boiling water or you're melting ice. Okay? So this can only happen when you have either they're both positive or they're both negative, and I'll show you why. So I'm going to set the delta G value equal to 0. Don't worry about the numbers. I'm just going to let that be delta H minus T delta S. I want to get delta T by itself. Okay, I want to find my temperature by itself. So I'm going to move this over, and I'm going to have T delta S equals delta H, and my temperature is going to be delta H over my delta S term. Now, this is where the magic happens. So my delta H is kilojoules per mole. My delta S is kilojoules per mole Kelvin. But the Kelvin is in the denominator of the denominator, so the Kelvin flips up. Hey, I get temperatures. Now, is Kelvin ever a negative value? No. So this is why this works mathematically. I can only reach a point of equilibrium where either my delta H and delta S are either both positives or both negatives. Because if I have a positive and a negative value for that, I get a negative value for temperature. Okay? So this is important. You can only find a critical temperature where it goes to equilibrium is if they're both positive or if they're both negative. That's it. Okay? Now, in this situation, I've got my delta H term, which we said was 10 kilojoules, and my delta S term was 20 kilojoules per mole Kelvin. So you do this, you get 0.5 Kelvin, which is a really, really, really cold temperature. Okay? But now, this is going to be a critical temperature. one of the most vital things you have to understand out of this thing. So notice that I have, in this situation, I had both of these being negative values. I had a negative delta H and a negative delta S. Okay, I have two negative values. So I'm going to come in here and I'm going to calculate delta G, but I'm going to let the temperature be 1 Kelvin because it's going to make the math work out nicely. Okay? So I'm going to have my delta H, which we said was negative 10 kilojoules, minus, and I'm going to let that be 1 Kelvin, and then I'm going to have 20 kilojoules per mole Kelvin. Okay? So if I do this, I'm going to take negative 10 minus 20, right? Okay? Actually, that's a negative 20. Okay, that's kind of an important part. That's a negative part. So I got negative 10 minus a negative 20 multiplied together. So in effect, I'm going to add that together. And so if I do that, what do I give for my delta G? Plus 10. So is my reaction spontaneous? No, because I have a positive delta G. So here's, if you look at this mathematically, some people like the mathematical approach to this. Basically, I can't let this T delta S term get too big. Because if that gets too big, then when I add it to that negative value, I shift it to a positive delta G. Now, let's say I'm going to do this again. Now I'm going to have negative 10 kilojoules minus, now I'm going to use 0.3 Kelvin, which is even colder, times the negative 20 kilojoules per mole. And so I got negative 10, and that's going to be 6. Now, here's the story. Now I've got a negative 10 minus negative 6. What's the sign of my delta G? Now I've got a negative delta G, and now it becomes spontaneous. So the only way that you can have a critical temperature is if they're either both positive or if they're both negative. So if it is that combination where they're both negative, and here's, you can always remember this. So negative people tend to make things low. Okay, it's like, man, it's kind of bringing me down. So on this sheet, where it's got for the reactions that are spontaneous at low temperatures, okay, that means your delta H is a negative value, your delta S is a negative value. Okay? So, and here's what you want to think through. The reason that that works is because I can't make the T delta S part get too big. That's why it has to be below a certain temperature. Now, I don't want you to look at that and go, oh, that only happens at cold temperatures. No, it just has to be below a certain temperature. That critical temperature might be 1,000 degrees Kelvin. You just have to be below 1,000 degrees Kelvin. So when I say low temperature, that's relative to the equilibrium temperature. That isn't saying, oh, it has to freeze. It just has to be below a certain point. Now, we're going to change it. And here's the last one. So now we're going to have delta G equaling my positive 10. Now I'm going to shift my delta H to be a positive value. So right away, what's my positive delta H? Endothermic, exothermic? Nathan?
Well,
Endothermic.
That's
Okay.
it.
Minus, and I'm going to have 1 degree Kelvin, and now I'm going to have a positive 20 kilojoules per mole. So here's the terminology. You would say the entropy term is driving it to spontaneity, because that's positive, The enthalpy term is driving it away from spontaneity because that's a positive value. So you have two conflicting ideas. The entropy term goes, hey, Mother Nature, I got you. I'll make a mess. The enthalpy term is going, I'm going to make you get cold. So basically, you're, instead of a hot mess, you're making a cold mess. Okay? Now, here's where the magic happens mathematically. So now I've got 10 minus 20. I get a negative delta G. The reaction is spontaneous. Okay? So now, and even if I go to 5, if I go to 10, if I go to 20, if I go to higher and higher temperatures, all I'm doing is making the entropy term bigger, which is going to make delta G even more negative. Now, get out of your minds right now that the bigger the negative delta G is, the faster it goes. There is no correlation between the magnitude of delta G in terms of being like a bigger negative value and the speed of the reaction. There is no correlation between those two values. Zero, zip, none, not, nothing. Okay. Now, but here's where the magic happens again. So now if I go 10 minus and I drop that to 0.3 Kelvin times 20 kilojoules per mole, now I've got 10 minus 6, which gives me a positive delta G. Guess what? Spontaneous. It's not going to be a spontaneous reaction because of the fact that we got too cold. So I can't let the T delta S term get too small, but then I end up with the positive delta G. So here's your combinations. If you ever make flashcards, negative delta H, positive delta S, always spontaneous. Okay, no exceptions, none, zero, zip. Positive delta H, negative delta S, never spontaneous. Okay, that dog is never going to hunt. Okay, you can make it happen, you just have to reverse the reaction. So where this might happen is that let's say that you want to make a tree. Okay, to make a tree, realistically, you need some carbon, some oxygen, some nitrogen, and some water. Okay, basic components of the tree. So you take a 5-gallon jug and you drop in some coal, which is your carbon source. Okay, you put in a little bit of water. Okay, you inject some air. There's your nitrogen and your oxygen. So you have the carbon's producing the coal. The air is providing the nitrogen and the oxygen, and then you have some water. And I promise you, if you take that 5-gallon container and shake it up for like 10 minutes, and then look at it, you are not going to make a twig.
Why?
Okay? Shocking as that may be. Which would be cool. It's like, oh, you want some firewood? Go get me some water and some coal. I'll put it in a container and I'll shake it around. I'll make some firewood. Okay? No! Okay? No matter what you do, that is never, ever, 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 ever going to happen. Never. Now, you can have a positive delta H and a positive delta S. Now, this is a situation where everything's positive. Positive people do what? They lift you up. Okay? So this has to be above some temperature. And again, this doesn't need to be the surface of the sun. It doesn't need to melt iron. It just has to be above a certain temperature. So if you look at melting ice, so here's the quintessential example. We're going to melt ice. So if you're going to melt ice, what's the sign of delta H? Colin.
Positive.
Why?
Because it gets cold.
Which direction does energy flow?
Into the ice.
Into the ice. So energy is flowing into the ice. So guys, it's an endothermic reaction. Isaac. What's the sign of delta S for melting ice?
Positive.
Why?
I'm making a mess with the liquid. That's right.
Yes, you're going from a solid into a liquid. Ah, there's the perfect combination, right? Positive delta H, positive delta S. Guess what? You have to be above a certain temperature. Now, the other combination is you have a negative delta H and a negative delta S.
Ooh, they tear us down, bro.
So that has to be below a certain temperature. So let's say we want to make ice. We want to make ice. So if you want to make ice, right? So you have water, right? Okay. What are you going to have to do with the water? You have to cool it down, right? But what do you want to have? What do you want to have happen to the entropy of the water to make ice?
Yeah.
It's got to cool down. So you got to make it less. You got to decrease the entropy, and you have to take energy out of it. So this is much like freshmen. You can't add coolness to freshmen. The only thing you can do is like remove nerdiness. So the same thing is true of water. I can't add coolness. I can just remove thermal energy from it. Okay? So if I want to make ice, I got to have water. I need the energy to flow out of that water. Oh, I need that to be an exothermic reaction. I need it to lose energy. I need it to decrease its entropy. That's why it has to be below a certain temperature. If there's ever 4 things that you just begin to memorize, it's these 4. You have to know these cold, no pun intended, without hesitation. Okay? All right, so shut that down for a second.